Okay, excellent. So we will be resuming the dynamic seminar for this week and for this term. And our first speaker is Fahad Panolin from IIT Hyderabad. Before Fahad moved to IIT Hyderabad, he did his PhD from the Institute of Mathematical Sciences in India, in Chennai, after which he was a postdoc at the University of Bergen, uh, following which he moved to Hyderabad. So Fahad has a range of work in parameterized complexity, graph theory, and approximation algorithms, the last of which he will be telling us about in this talk. So Fahad, uh, thank you for agreeing to speak. And whenever you're ready, the floor is all yours.
Okay, thank you, Amasa, and thank you for having me in your seminar. And what I will speak about is a low-rank binary matrix approximation, where the objective is to minimize something called column sum norm. And yeah, the problem will be clear within 2 slides. Okay, and this is joint work with Feder, V. Fomin, Peter Golovach, and Kirill, and it appeared in last year approx. So if you are interested, you may look into the paper, and anytime you are free to interrupt and ask me in case something is not clear. Okay, so so as I said, I will be talking about the low rank matrix approximation. And in general, what is this low rank matrix approximation problem? Given a matrix, I want to find a low rank matrix which is close to the input matrix. Okay, and or in some sense you can think that the given input matrix, you are compressing it, because the low rank matrix can be written as a product of 2 smaller dimension matrices. So it is, in that sense, it is a compression. Yeah, and this has a lot of application in machine learning and scientific computing, and I don't go too much into the application, and I will stick to the problem, the theory problem, and what we can do. Okay, so just formally define what is low rank matrix approximation. So the input is a matrix A. Okay, for the time being, it is on reals. Okay, and our work is on GF2 on a Galois field of 2. But just start with the reals. Okay, so given a matrix A and an integer R, I want to find out a matrix B which is very close to A, or in other words, some norm of A minus B should be minimized. Okay, and 2 important norms in this regard are, like, one of them is Frobenius norm, which says that look at the entry-wise difference and then take the square and take the sum of it, and that is one of the norm which is very popularly studied. And the other is a something called the spectral norm. Okay, the spectral norm says that how much worst case stretch can have on a vector. Okay, so if you take a unit vector x, now how much more like B will be stretching, like when you multiply bx. Okay, now that difference is captured by this expression. Okay, so you can think like a Frobenius norm is some sense an averaging error, or like in a spectral norm, it is like a worst case stretch. Okay, so, and in the case of binary matrix, it will be little bit more clear, that because it is more combinatorial there. Okay, and both these problems are solvable in polynomial time using singular value decomposition. Okay? And what we do is we consider the low rank matrix approximation problem on binary matrices, and the field is over GF2. So, so the idea here is like, or the problem here is as follows: given a binary matrix A, I want to find out a binary matrix B which has small rank, which means that I should be able to write it as C times D, and C dimension is M times R, and D dimension is R times N. Here, the product, these operations are over the field, GF2. So which means that addition modulo 2 and multiplication modulo 2. And so that is our objective. So given A, and I want to find out B, and that approximates A. Now, what do I mean by approximates A? Now, again, I can have the notion that some norm of A minus B is minimized, okay? And the minimization is over B having smaller rank. Now, one of the way you could think about is like the total number of entries mismatching between A and B. Okay, like you look into the first row, first column entry of A, and you see whether it is mismatching with B, and you count for all the entries and how many places you are mismatching, and that's called entry wise L0 norm. And that problem is called log GF2 rank approximation, and that is more or less similar to the Frobenius norm in the case of a real in the case of the real field. Okay? And for the column subnorm, an equivalent of that here will be the following. Okay, you look the first column of A and the first column of B and see how many entries are mismatching. Okay, and similarly second column of A, second column of B, and how many entries are mismatching. And the maximum mismatch between the corresponding columns, that quantity you want to minimize. And that problem I call it as L1 rank or approximation over GF2. So column wise you look for a like how many mismatches are there and take the maximum across the columns, and then you want to minimize that quantity. Okay, and so that is the problem. And so in this work we will be considering the second problem, L1 rank R approximation over GF2, and this problem was also considered, and I will talk about the results of both the problems, and we will move on to the column subnorm, like minimizing column subnorm, that problem. Okay, okay, so first take the first, like the entry wise L0 norm. Okay, that problem, law GF2 rank approximation. That means like how many entries are mismatched between A and B. And this problem is NP hard, and there is a deterministic PTAS with running time, as mentioned here. You can think here R being a constant and the epsilon is the error parameter. Okay? And two sets of two groups of people proved that a linear time approximation scheme is possible for this problem, but randomized, which means that it will take this k you need to take it as r, f of r comma epsilon n, n times m, where n is the number of columns of the input matrix and m is the number of rows of the input matrix. Okay? So this is what known about log GF2 rank approximation. It's NP hard and it has a EPTAS. Now, so we asked the question, the similar question about this problem, where I want to minimize column subnorm. So I want to get a small rank matrix minimizing the column subnorm. Okay, or in other words, in column wise, you just count how many mismatches are there and look for the maximum on which column it is maximum, and that quantity you want to minimize. Okay, and a simple reduction from using a simple reduction from closest string, we can show that this problem is NP hard. Okay, even for R is equal to 1. Okay? And our result in for this problem is the following. It admits a p-task. Okay, as again you think R is a constant. Okay, it admits a p-task, and it's a randomized p-task. Okay, so a randomized 1 plus epsilon approximation algorithm with running time, as I mentioned here. Okay, it's a huge running time. Okay, and at the end we will talk about whether we can improve this or not. Okay, in the conclusion. Okay? So next, what we will see is like some of the proof ideas of this result. Okay, now, so recall the problem. We are given a matrix A. I want to find out a matrix with rank B. Okay, all the operations are over GF2, and and I want to minimize this quantity, okay? The column sum now. Okay? Now, the high level overview of the proof is the following. Okay, first we reduce our problem to something called some kind of a case ender problem, which we call it binary constrained case ender problem. Okay, so from low rank matrix approximation to something called a case ender problem with some constraint, and it is our binary, like it's our GF2, so we call it binary. So binary constrained case ender problem. Okay? And then this problem we again reduce to something called binary constrained partition ender problem. That is a tiny difference, not too much. Like there is one more additional information is given in the input for the new problem. Okay, but how to get into that input is also require like some technical work. Okay? And then at the end, what we do is we solve this problem, whatever I call it, binary constrained partition center, using integer linear programming. Okay, or in other words, like what we do is we will formulate the problem in as a integer linear programming, and then we solve the LP relaxation of it, and then use the randomized rounding technique to get a good solution for the problem. Okay. And now come to the step one. Okay, in the step one, what I want to do is I want to think about this low rank matrix approximation problem where the column sum norm need to be minimized as a case ender problem with some additional constraints. Okay, so first look at how the what we want in this problem. So we are given a matrix A, which has n columns and n rows. Okay? And I want to have a matrix B. It should have rank, at most R. And if I look into the Hamming distance between A1 and B1, and then A2 and B2, and like that, and the maximum Hamming distance among all these AI, BI pairs, that should be minimized. Okay? Now focus on the matrix B. The matrix B, it is a rank R matrix over the field GF2. And such a matrix can be written as sum of rank 1 matrices, BI. So R matrices, B1, B2, etc. up to BR. So the B can be written as sum of R rank 1 matrices. So each BI is of rank 1. So what is the property of a rank 1 matrix in GF2? It will have one non-zero, like the number of distinct non-zero columns of BI is 1. There is like, so it will look like, one particular, 0, 1 vector and a 0 vector. These are the two possible columns possible for any BI. Okay. So each BI, you will have, like all non-zero columns of one particular BI are identical. For each I, all non-zero columns of BI are identical. Okay? Now, that automatically tells you that the number of distinct columns of B is 2 to the R. Okay, it's quite easy to see that. Okay, so the number of distinct columns of B is 2 to the R. Okay, now, so now imagine this is kind of a case ender problem where K is equal to 2R. Okay, how do I imagine this as a case ender problem? Okay, now look at A1. Okay, now these blue vertices are the distinct 2 to the R vectors here. Okay, so maybe B1 equal to B2. Okay, then this blue point is same as B1 equal to B2. Okay? And each AI, I look into BI, which is a particular 0, 1 vector, and to that group, you just put in that AI. So you can think that you have grouped these red vectors, which are the columns of A, and they are close to the blue vector, which is a one particular distinct column of B. And the number of blue vectors is like 2 to the R. So essentially what you like now, if you think in the reverse direction, what you want to compute is you want to compute 2 to the R. So let me call it K. K is equal to 2 to the R. 2 to the R blue vectors, and you want to and then you want to group all the vectors to the closest sender. So these blue vectors, I call it senders, and the red vectors are the input columns of A, and then you just group onto where it goes to closest, and then what is the maximum distance of a blue vector to a red vector within that group, that you want to be minimizing. Okay, and there is one more property we want. These blue vectors, that there are 2 to the R of them, the rank of those vectors should be R. Okay? So that is a constraint on the senders. So you can think it as a finding K senders, finding like now you can think about it as a K sender problem. So you are going to find K blue vectors and then minimizing, the maximum distance from blue vectors to one vector, like one input vector within that group. Okay, and but it has an additional property. You also need an additional property. These sender vectors have some should satisfy some property. That property is, that should be generated by R vectors, or the rank of those 2 to the R vectors should be at most R. Okay? So this is the, is this clear? Like, is this reduction? So now we are going to solve this problem.
Sounds reasonable.
Yeah. Okay. So the point is now I want to talk about what is this relation between these, cluster senders. Yeah. Now for that, okay, that's how we define something called a binary constraint K sender. So I will have some definition. Okay, after this definition, it will be clear to you what is this this relation between the senders. Okay, so I define. So I'm going to define a new problem, a K sender with some constraints. Okay, so what is this constraint? So suppose you think that you are given, n vectors. These are the columns of A. And the dimension of each of the vector is m. Okay, m is the dimension of the vectors. And additionally, you are given m relations, r1, r2, etc. up to rm. And each of these relation is a KRE relations. So each Ri contain lot of tuples, K length tuples. Okay? So then I can say that, then I will say that a set of vectors. So you could think that this C1, C2, Ck being the sender vectors. Okay? This satisfy this relation, this set of relations, R1, R2, etc. up to Rm, if the following hold. Okay? You just list out these sender vectors, C1, C2, etc. up to Ck, and look for the ith row in it. Okay? So ith row will give you a K tuple, and that K tuple should belonging to Ri. Okay? Then we say that, okay, this set of senders C satisfy the set of relation R. Okay? Now what I will say is there exist relations R1, R2, etc. up to Rm. Each of these Ri's are equal to actually one particular relation R, such that whatever the constraint I want for my low rank matrix approximation is same as satisfying these particular relation. Okay, just okay, before going into that, I will give you like an example of like a bunch of vectors, K vectors satisfying a relation. Okay, just take, m is equal to 2, K equal to 3, and just take two relations, R1 being this, R2 being this, and look at these three vectors. So C1, C2, C3. We can say that satisfy this relation, R1, R2. So how do you check? You look for the first row. First row, you can see that 0, 0, 1, and that belonging to R1. And second row, you look at the second row, that is 1, 0, 1, that belonging to R2. So this is an example of like what is meaning of a set of sender vectors. satisfying, a set of relations. Okay? So notice that I just used the set notation, but here order matters. Okay, so think that it is ordered set. Okay. Okay. Now the binary constraint case ender problem, I have given, n vectors, each of length m, and also given r relations, m relations. And I want to find out, case enders satisfying r, and I should be able to, and I want to minimize something similar to the case ender, objective. And that is what is written here, a case ender objective. The shortest distance from X to one of the sender and the maximum amount that should be minimized. Okay. Now I'm going to explain to you like how I can, convert this binary matrix, our problem where I want a low rank matrix minimizing column sum norm to this particular problem, binary constraint case ender. Okay. So our objective here was like, the matrix is given A, and it has, n columns, and we want to partition these columns of A into 2 to the r parts. In each of the part, I want to find a sender vector, and these senders should, it should have a linear span, like it should have rank at most r, or like senders for each part such that senders are linear span of r vectors, and minimizing the case ender objective. Okay, now I will tell case ender objective. So I don't, talk about this long sentence. So I hope that is clear to you. Okay? Now take an example of r is equal to 2. Now I take every like r is equal to 2, and for each m, for each I in m, the vector, the relation ri to be 0, 0, 0, 0, and then 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0. Okay, now how you can visualize it is like, the third or the fourth entry is the sum of the, second and third. Okay, so essentially it is the linear span of the, like the third will be the linear span of the second and third, and the first corresponds to the zero vector. Okay, so now any vector, any any set of 2 to the r 4 vectors, okay, c1, c2, c1, c2, c3, c4, that where every row satisfies these constraints will have rank at most r, like rank r, or at most r is equal to 2, because you can see that c4 will be sum of c2 and c3, okay, and c1 will be 0. Okay? So that way you will get, so any 4 vectors which satisfy these relations on every row will have rank at most r. Okay, so this is the way, like, so I can come up with, and this can be generalized to any r. Okay, I will have 2 to the r tuples here. So for r is equal to 2, I have 4 here. For a general r, I will have 2 to the r tuples here. So I will not go into the technical details of it, but essentially this is the same idea. Like you can have various linear combinations after r plus 1. Okay. So that is what, like, so now I can think my low rank matrix approximation, minimizing column sum norm, same as a case ender problem with some binary, like some constraints. Like the constraints are encoded as some relations. So that is the, that is the first reduction I said. Okay. Now the second one is very simple. Like second one, you can think it as like, okay, what is the second problem? Like I'm going to reduce to binary constraint partition sender. Okay. In the partition sender problem, notice that you want to find out these k clusters and the k senders. Okay. So you want to find out k senders as well as which all the input vertices goes to which clusters. Okay. In the binary constraint partition binary constraint partition case ender problem, you are also given the partition of the input into k blocks. Your only job is to find out these case enders. So additional information is provided. How the inputs are clustered, like how the inputs are clustered is given to you, and you just need to find out these k, k sender vectors. Even that is very hard. Like if you notice, k being 1, it is same as the closest string problem. Okay? K being 1 for this problem is same as closest string problem. Okay, so one more additional information is given in the input, like how the inputs are clustered. The only job is to find out these senders, satisfying R and minimizing this, k sender objective. Okay. Now this is like, I'm not explaining this term. This you can think it as k sender objective. Like, so you, from a sender, you need to draw a circle, and what is the radius of that circle, and that should cover xi. So from ci, you will be drawing a circle at a radius, like with a minimum radius covering xi. And what is that radius? Maximum that radius you need to minimize. Maximum over I going from 1 to k, and that quantity you want to minimize. Okay? And the technical term is written here. Okay, now, okay, so the here I want a reduction, like, so in binary constraint case ender problem, this partition is not given. In the second problem I explained, binary constraint partition case ender problem, we want that partition. Okay, so how do we come up with that partition? Okay, now to come up with that partition, we do something called the dimension reduction technique. Okay, using dimension reduction technique, we will do that second step, how to get the partition of X into clusters. Okay? So this is an equivalent of a Johnson-Lindström lemma in the case of a GF2, in the case of GF2. Okay? Okay, so what is this says is, suppose you are given n plus k vectors, binary vectors, like dimension m, and you are also given a vector, a error parameter epsilon, then there is a linear map from y to a smaller set of, like a set of vectors whose dimension is small. The dimension is log n, and the constant depends on epsilon. Okay, so you can reduce that, like you can reduce the dimension of every vector to roughly order log n, such that between every pair of vectors in y, their relative distance is preserved, okay, or with high probability. Okay, or in other words, there exists an alpha, a number alpha, such that the distance I'm talking about here is Hamming distance. Hamming distance of dxy, like look at the Hamming distance of phi of x and phi of y, and that will be sandwiched between 1 minus epsilon, the distance between, Hamming distance between xy, and 1 plus epsilon Hamming distance between xy. And there is a alpha here because, see, if in y I have a vector all 1 and all 0, then I have Hamming distance 0, and Hamming distance m. And if I have, only log n many dimension, then that distance will be at most log n. So I want this to be relatively preserved. So there will be some number alpha according to which this will be preserved. So the alpha is, there exists alpha such that for all xy in y, relatively the distances are preserved. Okay? So this is the equivalent of Johnson-Lindström lemma in the case of GF2.
Fahad, a couple of quick questions. So what is K here, and what does alpha look like?
Okay, like like K, I wrote it here. Like you can forget K here. You can say it is 2, like n. N plus K is equal to capital N, and this small n is capital N. Okay, so because I want to explain this for my problem, like and then I have n input vectors and k centers. So I just keep that parameter. Okay. So essentially you can forget about k here and the lemma holds. Okay. Okay. When I apply like this lemma, I am taking like the number of vectors y here to be n plus k. Okay, that is my input vectors and k centers. Okay. So yeah, because since I'm using for that, I just wrote it like that to be clear. Okay. So is that clear?
Yeah, and about alpha?
Alpha, we don't need to know the alpha. So the only point I want to know is like which vertices are closer. Okay, alpha is a number. Okay.
Right.
So I'd say like there exists an alpha such that for all x, y in y, this holds. Okay.
Right,
so
but
alpha
do you...
is like some factorizing number or a normalizing number. And I don't use it at all. And this linear map of phi is very simple, which is a random 0-1 matrix where the probability depends on epsilon for each entry. Okay, so I don't go too much into the detail, but it is very simple.
Okay.
You just make
Thanks.
it in. Thanks. So I hope this is clear, like what it is doing. Okay. Now, so what is now how I am going to use? So notice that I'm given x, I don't know c, okay, and I want to give a partition of this x such that these senders are like these clusters are correct, and later I am going to find out to c. Okay, so this is the objective. So in this step, I want to find out this partition of x into k clusters. Okay, now what do you think is, you think y being x union c, where x is your input vector and c is your unknown k centers. Okay, and then you apply this lemma, you apply this phi, linear map of phi. Okay, and what does it say? The relative distance between any two vectors in x and c are preserved here. Say if y1 and y2 in x union c are far apart, originally far apart, then after taking linear map also they are far apart. If they are close, then they are close. Okay, but by this kind of a factor. Clear? So now, but I don't know c, but I can guess phi of c. Why I can guess phi of c? Look at the dimension of phi of c. It is log n, a constant times log n. How many possibilities are there? N to the power order 1 by epsilon to the 4, right? So I can guess which is this phi of c. I don't know small c, but I can guess phi of c. Okay. So what I'm going to do is, I'm going to guess these vectors, phi of c1, phi of c2, phi of c3, etc. up to phi of ck. Okay, and then I know phi of x. X I know. So phi of x1 I know, phi of x2 I know, phi of x3 I know. And then according to, like, after doing that mapping, like I make a partition of that phi of x based on like where it is going to, like whether it is going to phi of c1 like close to that, or phi of c2 or phi of c3 like that. And then you will get a partition of phi of x. That partition I can project back. Yeah, and I'm not going to lose too much in the distance when I project back because of this guarantee. Because there is a guarantee of 1 plus epsilon here, 1 minus epsilon here. Okay, and too much numbers I'm not talking about, but you can see that there is a guarantee there. So, or in pictorially, okay, I know these red points. I want to find out these blue points, and I want to find out this partition. Okay, first I'm going to find out this partition, not this partition, some partition which is close to this. Now you do this mapping phi on these red vertices and blue vertex. Blue vertex you don't know, but you can guess where it is mapped to. This is the green, phi of C1. This you can guess, and phi of C2. This you can guess. Okay, but you know, a red point here will not go into the third cluster because that is too far. Okay, but something from the second one, which is close to here, which you can see, that may be moved towards the third. And you can notice that their distances are not, you know, not like this distance is not too much compared with the distance between this and this. Okay, and then only it will be able to move towards that because distances are preserved. So this is the partition. Now I know this green, but I don't know blue. According to green, you just partition the red vertices or phi of red vertices and project back to, you know, the red vertices, not vertices, red vectors. Okay, is it clear? Now you got this partition. Okay, now what you can prove is like, you know, any 1 plus epsilon approximate solution according to this partition will be 1 plus epsilon square approximate solution for PCs. Notice that I'm going to work on the original problem only. Like I'm just going to get the partition from here, and then later I'm going to solve it. But when I take the partition, I don't get the exact partition. Something may be moving, and because of that something moving, you know, there will be an additional 1 plus epsilon factor. Okay, so if you are taking an optimum solution here, that will be 1 plus epsilon solution, you know, approximate solution. Again, I'm not going to talk about numbers. Numbers will be boring. Okay, the intuitive idea is this. Okay. Okay. So that is what. So now you can think the following, right? So the input vectors is given, which is the columns of A, and the partition of it is given, and your objective is to find out these senders, and the senders should satisfy these constraints. The constraints are encoded using that relation. Correct? Now, how we are going to solve that? Okay. So that is the problem: binary constraint partition K sender. So input vectors are there, and K partition is there, and there is, you know, a bunch of relation is there. I want to find out, you know, K senders. Senders should satisfy the relation, and the K sender objectives need to be minimized. Okay. So for that, we use, you know, as I mentioned before, we just write this problem as a integer programming problem, and then we use, you know, LP relaxation, solve it, randomize it, rounding. And this method was previously used in the case of a PTAS for clauses string. So this is an extension of that. Okay. Now you can think that, you know, this problem is something like a, you know, finding K clauses strings, not instead of one, but there are some constraints also there. Okay. So the method is an extension of what is done for clauses string. Now, so we actually do it, you know, in two cases. And once when opt is large. Opt is large means opt is at least m by c, where c is a constant. What is m? M is the dimension of each input vector. Okay. And when opt is small, we are actually going to reduce to this case one by doing something. Okay. So I will mostly focusing on this one, you know, this case. Okay. So I want to write this as a integer programming. Okay. So what I do is, so now think about what is the problem. You want to find out the K vectors, right? K sender vectors. And if you look row wise, each of them is a tuple which belonging to Ri. Look at row I of these K vectors which are listed vertically. Look at the row I, and that should be a tuple in Ri. That is the constraint I am worried about. Okay, and of course I need to minimize, you know, the K sender objective. Okay. Now, so what I will do is for each row j, okay, row j, And for each tuple t in Rj, I will have a variable yjt. And the interpretation of yjt being 1 is like, okay, in the jth row, you are going to see t. In the jth row, what is that tuple? That tuple is c. That tuple is t. Okay, that is the interpretation of yjt being 1. Yjt being 0 means that is not the case. Something. Okay. So that is the interpretation. Okay. So now what you need is like, okay, look at this. The first constraint. What does it say? Look at a particular row J, and I want to choose one of the tuple in Ri, and the remaining should be 0. One of them is 1 and the remaining is 0. And whichever is 1, that is going to be that particular row. Correct? So I want a constraint like this. Among all the tuples in Ri, I'm going to pick 1. And that is the constraint written here. Okay. Now, notice that once I have these yjt values, I actually know what is Ci, what is C1, what is C2, what is C3. Correct? If I know yjt values, the moment I know yjt values, I know what is C1, I know what is C2, I know what is C3, like that. Okay? Then I can write distance between x and C1 as a linear function. Okay? I mean, I won't go too much into how you write the linear function, but this quantity, like you can see what I marked, right? The blue thing. Okay? So that is the distance between a vector x in xi and the sender Ci. So notice that Ci is well defined the moment I have yjt values. And that is a linear function. You can work it out. That is a linear function. Okay? And what is the objective? I want that quantity to be minimized. So there exists a D such that for every x in xi and I in k, the distance between Ci and x need to be minimized. So how do I write? I write this is less than or equal to D, and I want to minimize D. Okay? And of course, this is 0, 1 random variables. And this, like, if you are interested to look more technical details, you may read this. Okay, how I'm writing this distance. So the only point, the moment I know yjt, I can write distance between x and Ci as a linear function. Okay. Due to lack of time, I don't go into too much of those details. Okay. So you can think like x is a fixed vector here. Only yjt values. These are the variables, and this quantity is either 0 or 1 based upon t. Okay. So that's why this is just like summation, and then there is a coefficient here, and only once yjt appear there. Okay? So it is a linear function. Okay? So this is the way you can write BCPC problem, binary constraint partitioned case-center problem, as an IP, integer programming. Okay? Now what we are going to do is, we solve this LP relaxation. So instead of finding 0, 1 vectors, it is between 0 and 1. Okay? So yjt is greater than or equal to 0, less than or equal to 1. And we obtain fractional solution yjt star. Okay. Now, look at a particular row J and look at all values of yjt star where t varies. What does it mean? The first constraint says that is equal to 1. Correct? So varying over t for a fixed j, and that summation will be equal to 1. Okay? Which means that you can think for a fixed j, these values yjt star being a probability distribution, because they sum to 1. And that says with what probability a particular TB likely to be occur, right? So then what you do is you are going to sample according to that distribution and fix one of the t for that j. Is that clear? for a particular row J, look at Yj T star, where T values are varying, say T1, T2, T3, T4, okay? Yj T1 star, Yj T2 star, etc. And these values, when you sum it up, you will get 1. Okay, so this is a probability distribution over the tuples in Rj. Okay, so you are going to do, independently with the probability Yj T star, you are going to set Y prime Jt to be 1. Y prime Jt to be 1. What is the meaning of that? In the jth column, you are going to set T. If this is going to happen. If you are going to set 1, then you are going to say in the jth row, look at my center vectors in my jth row, it is equal to T. Okay. So this is the randomized rounding step. Is that clear to you? Okay. Then what we do is, then what we got is like, okay, now you got an integer solution, right? The only difference is this may not be satisfied. Okay, so this is satisfied because the way randomized rounding I did, this is satisfied. Okay, and this is also satisfied, the last one. Okay, but this may not be satisfied. But using Chernoff bound, we say that the probability that this is going beyond d plus epsilon d, where d is the optimum, is that is quite small. Okay, so this is not satisfied, but we say that this will not go too much far. It will go an epsilon away from it. Okay, for that we use Chernoff bound. So that is the climb. This quantity like y prime jt, this is a 1 plus epsilon approximate solution for my IP. Okay, my IP solution can be directly translated to my binary constraint partition center, right? Okay, now just give me a minute, 1 minute. Okay, sorry. So now, as I said before, this is the distance between X and Ci, this quantity. I want to see like how far it is going. I don't want this to go too far. Okay? So I will look into the expected distance of X and Ci. That is the expected Hamming distance. That is, you could see this is the same expression. And the expectation of this is a random variable, right? Y prime jt is getting 0 or 1 value. And the expected value of this, and the expected value of this is actually same as y star jt, because that is the probability you are going to set it, right? And what is this equation? This equation is same as this equation, correct? So what does it say? Expected distance between X and Ci is bounded by D. Correct? So the expected distance between D and Ci is bounded by D. So if you are happy with the expectation, then this is an algorithm. This is done it. Okay. Now, if you want things to happen with high probability, then what you do is you just fix a constant delta being epsilon by C, and look at each of these. This is a random variable. This summation, inner summation, it is a random variable. It is a 0, 1 random variable. Oh, sorry. This quantity, this is what the distance is, right? This quantity, the inner summation, is a 0, 1 random variable. Okay, and there are m such random variables, and they are all independent, because for each row I'm going to do the random process differently. Each row, they are like row 1, row 2, they are independent. So I will have n 0, 1 random variables. Using that, what I can say is probability of this is going away from D plus epsilon opt, which is upper bounded by D plus delta M. There I use opt is at least M by C. Okay. Now, and that is upper bounded by e to the power minus some constant into M. And this is Chernoff bound. And where does m comes? M comes m01 random variables. For each j in m, I have a 0, 1 random variable, and that is what the inside summation. Okay. Now, then what you do is you just do union bound and then say like, okay, there exists I in k and x in xi. What is the probability that this is going with this is upper bounded by n times this. Okay. And this is upper bounded by n to the 1 by n square if m is at least log n, some constant times log n. Because when it is some constant times log n, I will get 1 by n to the some constant. Correct? Now, if m is order log n, things are easy. I can guess. Okay, you can just think about it. If m is log n, guessing k centers is good enough. That will be like n to the k. Like there will be another constants also. Okay, so this is so a randomized rounding will give you a good approximate solution with high probability. Okay, and in the case of optimum less than m by c, maybe since due to lack of time, I won't explain to you. The point is like initially I will fix some coordinates, some rows, what are the values for the center vectors, and then I just prune towards what is not fixed. There I could see that optimum is large. Okay, so there is a method with which we can do it. Okay, so since lack of time, I won't explain that. Sorry, this is case 2. Okay, so there is a method, there is a reduction from the case 2 to case 1 by fixing some of the coordinate in the center. And that anyway, I didn't add more slides. I know that there won't be time. Okay, now I just conclude. Sorry, I just took 3 minutes more. So we gave on a PTAS. The running time will be this. Okay, so there will be epsilon here, 2 to the power 4 are here. Okay, I didn't do analysis, but this is the running time. And naturally, we can ask the question whether I can get f of epsilon and mn to the power some function of r. Can I remove epsilon from the top here? And actually, one can prove that that is not possible, assuming FPT not equal to W1. Just adapting similar result from closest string. And again, adapting similar result from closest string, you can say that you can't even do little of 1 by epsilon decrease even for r is equal to 1. Assuming exponential time hypothesis. So, but still there is an open problem here. This does not talk about whether can I remove this r from here. Can I have f of r comma epsilon, and on the top I don't have any function of r, but just epsilon and some constant independent of r, and that is still open. And since you cannot fully avoid this 1 by epsilon from this top, and for that things will fail. ETH will fail, and yeah, but this is an open problem, and that's an open problem in this, and that's it.
Okay, excellent. Thanks a lot for the very nice talk. So, are there any questions for Fahad? So while we wait for other questions, Fahad, I had a couple. So could you go back to the slide, the previous one with the open? So this running time in the last point, am I correct that you achieved this running time for this point-wise L0 norm problem?
No, the columns are no.
No. So the last question, so the last running time at the bottom. So you said that you also talked about this point-wise or coordinate-wise L0 norm.
There actually a linear time is there. Like I mentioned that a linear time PTAS is E.
Okay. So that was just MN.
Yeah, that was just MN. And this is, Yeah, this is the more difficult problem, like computationally difficult problem, harder problem.
Okay, and my other question was, could you comment on, sidestepping the randomization?
See, the main place we use it is randomized rounding. Okay, so now I don't know, is there any method where we could actually use IP formulation in a different way for this problem to get it. Okay, and I think that problem, like I think first it is better to remove this randomization for the closest string because that is more easier. One, there are no constraints, only one center, and even that works on this particular IP thing. Okay, so now and oh no for that there is a no, if I remember correctly, let me. No, I think for the closest string, there is a method of de-randomizing it, but I think it won't be linear. And for this one, I don't know, maybe it is possible.
So when you say it won't be linear,
I think like it won't be anyway linear. It won't be, sorry, like just keep aside. I think for the closest string, there is a method where they actually block together and then try to do like parts by parts. So maybe possible. Yeah, I like it.
okay, so so far just to clarify, so there is a deterministic algorithm for closest string.
Yes, that's what
okay.
if my memory is correct, that is the case.
Okay, thanks.
And if I remember correctly, they just, made into different chunks of log n size and then did locally solving in each of the chunk and then something like that they did.
Okay, thanks for
and here I think like at some point we tried a bit of it, but actually this problem is like for the case 2 it is a bit more complicated. These okay. Distances are not just one distance, one common distance. These d is changing according to x for case
okay.
2. Okay, and okay. I think that is the place we had a difficulty for approaching that technique. I mean, I sorry, like we tried 1 year ago and then.
Sure. Thanks for is there any other questions? Yes, Dimitri.
Yeah, thank you for the talk. I was just wondering, suppose your R is big, but I'm kind of happy to to have some poor dependency on like epsilon and things like this. Like if R is big, what are good approaches to problems like this?
I think R is good, and if you can instead of 1 plus epsilon, if you look for 3 plus epsilon or something,
yeah,
then I think there is some simpler algorithm. Okay. No, I don't remember actually. Sorry, that is the case. I was okay. Like no, sorry. What I was saying will work out.
Dimitri,
yes, you can get this kind of running time if you want 3 plus epsilon.
All right, so I could get something like this if well, if I'm not going for, I don't know, 1 plus epsilon, I'm going for like a 4 approximation, yeah. Right? So something like this is possible. So it's f of r times, poly of m and n.
Yeah, that is possible.
Yeah, very nice. Okay.
And I took, I tried for 2 plus epsilon, and that's the place I got stuck.
Okay,
got it. Thank you.
Okay. Thanks, Dimitri. Thanks, Fahad. It was a very nice talk to start the NAP seminar this term. So thanks everyone for joining, and see you all at the next NAP seminar.
Okay then, bye.
Thanks, Fahad. Good to see you. Bye-bye.
Thank you. Take care.